Okay, so in this video we're going to take a look at position equations from accelerated motion, but first let's talk about average velocity because we're going to need to use it. So if Marty McFly the physics fly is traveling 10 meters a second, later he's traveling 14 meters a second, what is his average velocity? If you were going to try and solve this without really knowing anything about physics and just sort of using raw math, you would say, okay, the average velocity is just 10 plus 14 divided by 2. Right, because that's the number of velocities, so you divide by 2. Well, we can write that as a little equation for ourselves. First, let's write v with a bar above it. That means that it is the average velocity. And we would write the, let's say, I don't know, v plus v naught, the final velocity plus the initial velocity, and then divide that by 2. And boom, we have an equation for average velocity. Let's see if it works. Okay, 14 meters a second plus 10, divide that by 2, so that's 24 meters a second over 2, or 12 meters a second, which is the average velocity. Pretty easy. Okay, we're going to use this average velocity equation in just a second to find a position equation. So remember that the only position equation we know right now is a position equation for constant velocity whenever there's constant velocity. So it looks like this: x equals the average velocity plus times time plus the initial position. Okay, so this is the equation we use to find how far something has traveled, or the position that something is at, if we know what its average velocity is. And when we know that the object is moving at a constant velocity, I know that the average velocity just is that constant velocity. Well, now I have a way of understanding what to do if the average velocity is not necessarily the same as the velocity in the beginning or the velocity in the end. We use this little average velocity equation we just got. So if I plug that in here, I'm going to get v plus v naught over 2 times t plus x naught. And if I wanted to pretty that up a little bit, I would write x equals 1/2 v plus v naught t plus x naught. Okay, so this is an acceptable equation to find the position of an object if something is accelerating, meaning it has an initial and a final velocity that are different. Remember that delta x, or any delta, is just the final minus the initial. So if I wanted to, I could subtract x naught from both sides and get x minus x naught equals 1/2 v plus v naught t, v naught times t, and then rewrite this left-hand side just as delta x. So sometimes we will see the equation written like this, where I have the initial position on the right and the final on the left. But other times it might be easier to just think of it in terms of not what is your position, but what is your displacement. So that is another way to write the equation. Okay, let's do an example with this. Bill Eyelash is at a stoplight when they decide to floor it. After 10 seconds, Bill has the zoomies going 40 meters a second. How far has Bill gone in that time? Okay, well here, I know that I'm at a stoplight, which means, or Bill is, the initial velocity is 0. And later, we have the zoomies of 40 meters a second, so that can be our final velocity. It gives me a time, so I know that that's the amount of time it takes. And it wants to know how far. So to me, that means find delta x, the displacement. And if delta x happens to be negative, the far means just ignore that negative and give me the number of that displacement. We'll see if that matters after this problem is over. Okay, so now I have v naught, v, t, and delta x, and I can use this equation that we just derived. Half of 40 plus 0, so basically that's the average velocity, times time, the 10 seconds. Okay, 40 plus 0 is 40, and 40 divided by 2 is 20, and then 20 times 10 is 200. You want to write that out for a second? Basically, if I carry the 1/2 in, I'm going to get 20 meters a second times 10. Seconds cancel out. 200. Okay, so I know that Bill has gone 200 meters. Great job. Let's take a look at a new position equation that we can get. Okay, so let's start with the exact same equation that we had last time. X. Oh, there's the bell. X equals average velocity times time plus x naught. But now instead of replacing the average velocity equation, wait, sorry about that. Take the average velocity equation again and plug it in so that we get v plus v naught over 2 times t plus x naught. But we're actually going to do one more substitution. What we're going to do is we're going to take this equation for accelerated motion, and we're going to plug it in for v. Before we do that, let's take the 1/2 out again. Okay, so it looks like what we had before. And now we're going to plug in v. So we get 1/2 at plus v naught plus v naught times t plus x naught. Now I'm going to do a few simplifications. The first thing that I'll do is I will combine these so that I get plus 2 v naught. And then I'm going to distribute the 1/2 and then also the t. So I'm going to get 1/2 at times t, so t squared. And then I would get 1/2 times 2, which is just 1, so v naught, and then times t plus x naught. And here we have a new equation that we can use to find the position of an object if we know its acceleration, and we should put a little average bar on there, its acceleration, its initial velocity, and its initial position. Again, if I want, I can take advantage of the fact that displacement is x minus x naught, so if I just subtract x naught from both sides, then I can write delta x equals 1/2 at squared plus v naught t, which is another way of writing this same equation. Sometimes it'll help us to use that, sometimes it won't. It depends on the problem, but we'll see how that works out. Let's do an example. Marty McFly, the physics fly, is 4 meters left of a Taco Bell and traveling 2 meters a second to the right when he begins to speed up at a rate of 4 meters a second squared. What is his position after 6 seconds? Okay, so first, the fly is 4 meters left of the Taco Bell, so I would say that's my initial position, and it's negative 4m. I used negative because it says left. Then I see that he is traveling 2 meters a second to the right, which gives me an initial velocity. And I might put a little positive to remind myself that it's to the right. Then the acceleration is 4 meters per second squared, and I know that it is also positive because it says that he's speeding up. And if my initial velocity is positive, then in order to speed up, my acceleration has to be in the same direction, which would be positive. And there is a time of 6 seconds. Okay, so now I would use my new position equation, and we can call that the average acceleration. Sometimes I just get lazy and forget the bar. Okay. So now I would do half of 4 meters a second squared times 6 seconds, the whole thing squared, plus 2 meters a second times that 6 seconds, plus negative 4. Okay, now I go through and I work on all of these terms. Half of 4 is 2, so that's 2 meters a second squared. 6 seconds times 6 seconds is 36 seconds squared. And then I'll write this 2 meters a second. Won't worry about that in a second. Or 6. Okay, so the first term, these second squareds cancel out, so you'd get 2 times 36, which is 72 meters, plus 2 meters a second, the seconds cancel out, times 6 is 12 meters. And then minus 4, because that negative is there. Okay, so 72 plus 12 is 84, and then when you take away 4, you are left with 80. So the final position of Marty McFly is 80 meters. Congratulations, you have used your 2 new position equations for accelerated motion. You did a great job. This video is over.